Have you ever noticed how the smartest AI models out there right now sometimes seem to just completely overthink the absolute simplest problem?
Oh, absolutely.
Like you ask it a basic question and suddenly it is spinning out these endless paragraphs of thought, almost like it is pacing the room before finally giving you an answer.
Yeah, and it is burning massive amounts of computing power doing that.
Yeah.
And honestly, the frustrating part is that it doesn't always lead to a better result.
Right.
Sometimes the model just gets completely lost in its own head,
Yeah.
you know, just generating line after line of text that doesn't actually move the logic forward.
It is like watching someone write a doctoral dissertation when you just ask them for the time.
Exactly.
But, well, what if we could teach AI to stop that endless rambling and actually start planning a little more like a human being? Today, we are taking a deep dive into a fascinating state-of-the-art paper from the Gen AI
It's a
archives.
really incredible piece of research.
Yeah, it's titled Efficient Agentic Reasoning Through Self-Regulated Simulative Planning.
Which I know is a very dense title, but the implications are huge for you listening, because the researchers are introducing a brand new AI architecture called SR2AM.
Right.
And this paper, it directly challenges the dominant approach in AI development today.
You mean the approach where developers basically just throw mountains of data and compute at a model and cross their fingers?
Yeah, pretty much. That is the dominant philosophy right now. The industry basically relies on the hope that if you make a model big enough and you feed it enough processing power, good planning will simply emerge from the chaos.
Which is a huge gamble.
It is. But SRAM replaces that hope with a deliberate three-part cognitive system. It represents a fundamental shift in how we actually structure machine thought.
Okay, let's unpack this. Because to understand how SRAM fixes this whole overthinking problem, we really need to understand why current AI gets stuck in that loop to begin with.
Right.
You called it unregulated deliberation when we were looking at the notes earlier. Let's define what that actually means.
So unregulated deliberation is the core issue with standard large language models today,
Mm.
especially the ones using, chain of thought reasoning.
Okay.
They operate as what we call reactive policies. Before they take an action, they generate this block of text, which is a latent deliberation variable.
Wait, let me pause you there. A latent deliberation
Yeah.
variable. That is essentially just the AI generating a stream of text as a proxy for thinking, correct? Like it's typing out its thought process.
Yes, exactly. It's generating words to bridge the gap between your prompt and its final answer.
Yeah.
But here is the critical flaw.
Okay.
There is no internal mechanism to control the presence, the horizon, or the structure of that planning. It has absolutely no structural awareness of what it's doing.
So it is literally just a stream of consciousness.
Yep.
It thinks, but it doesn't know how to think about its thinking. It doesn't know when to stop.
Right. It just churns out tokens endlessly. And during complex tasks, this leads to a dramatic increase in token consumption.
Which costs money.
Exactly. It's generating thousands of words of internal monologue without any guaranteed accuracy gains. It's highly inefficient and incredibly expensive.
So enter the fix SRAM. This is where the researchers decompose the AI's decision-making into three interacting systems. Let's walk through these because this is where it gets really interesting.
Yeah, so they broke the architecture down into System 1, System 2, and System 3.
Oh, wait.
System 1 is reactive execution. You can think of this as handling the fine-grained reasoning and direct action. It's the quick, free-form, messy stuff.
The gut reaction, like if I ask you what 2 plus 2 is, you don't need to build a spreadsheet to tell me it's 4, you just react.
Exactly. Then there's System 2, which is simulative reasoning. This is the actual planner.
Right.
Instead of just unconstrained typing, System 2 uses an internal world model to predict the consequences of proposed actions. It looks at the current state, proposes an action, and predicts the future state.
So mechanically, how does an AI build a world model? Because that sounds a bit like science fiction.
It's actually a lot like playing chess.
Yeah.
Before you touch a piece, you picture the board. You imagine moving your knight, and then you imagine how your opponent will react and what the board will look like after that exchange.
Right, you are running a mental simulation to update your world model.
Exactly. And standard AI doesn't usually do that. It just blurts out, move the knight, based on pattern recognition from past games. System 2 forces the AI to create that internal sandbox, test a move, and evaluate the predicted outcome before acting.
That predictive ability makes so much sense. But the real magic seems to be System 3, self-regulation. This is the configurator.
This is the piece that's been missing in AI. System third decides when and how deeply the agent needs to plan at each turn.
Wow.
It prevents the AI from falling into the trap of unregulated deliberation we talked about earlier, but it also avoids the rigidity of always-on planning.
Okay, I love a good analogy, so let me try this one out to ground this for you listening. It is like driving a car.
Okay, let's hear it.
System I is your hands on the wheel, right? You're reacting to traffic, tapping the brakes, changing lanes. That's the reactive execution.
Right.
System 2 is your GPS. It's simulating the exact route, predicting traffic jams ahead, telling you where you'll be in 10 miles. But System 3 is you, the driver, deciding whether you actually need to look at the GPS right now, or if you already know the way to the grocery store and can just drive based on instinct.
That analogy holds up perfectly, actually.
Yeah.
What's fascinating here is that while previous systems have tried to address parts of this,
Right.
like some had rule-based workflows, others had external controls, none of them combine all three into a unified architecture. In SRAM, the planning is both simulative, like your GPS, and entirely self-regulated by the AI itself.
Like the driver choosing when to glance at the screen.
Precisely.
So we have this elegant three-part theory. But the real question is, does it actually work? Does it save compute power while keeping the AI smart?
I'm looking at the performance tables from the paper here, and the numbers are wild.
They really are. But before I misread these, let me make sure I understand the core metric, the pass at one score. That basically means the AI got the correct answer on its very first try, correct? No second chances.
That is the standard definition, yes. One shot, one accurate answer.
Okay, so let's look at the two versions of this model they built. The first one, version 0.1, is a relatively small model. It has 8 billion parameters, and it's built on the Qwen 3 8B architecture.
Right.
Across 11 different benchmarks, it achieved an overall pass at one score of 57.0.
And to put that in perspective, for an 8 billion parameter model, hitting a 57.0 makes it competitive with standard large language models that have anywhere from 120 to 355 billion parameters.
Wait, really? A model that small is competing with 355 billion parameter models?
Yes, it is punching incredibly far above its weight class.
That is insane, and it gets better with the bigger version. I'm looking at version 1.0, which has 30 billion parameters. This one hit a pass at 1 of 71.3. That puts a 30 billion parameter model in the same ring as massive, 685 billion to 1 trillion parameter models, like DeepSeek v3.2 and Kimi-K 2.5.
Yeah, and we have to highlight the staggering efficiency here, not just the accuracy. The V1.0 30 billion parameter model consumed between 25.8% to 95.3% fewer reasoning tokens than competitive agentic models.
Up to 95% fewer tokens. That is a massive reduction in computing cost. I mean, that's huge.
Let's look at a direct comparison to make that concrete. The researchers tested it against another model called MiroThinker V1.5, which also has 30 billion parameters.
Yeah.
SR2AM achieved competitive accuracy. It scored 71.3 versus MiroThinker's 74.2, but SR2AM used 51.2% fewer reasoning tokens.
Wow.
It used about 5,500 tokens compared to MiroThinker's 11,300. It is delivering basically the same caliber of work with half the cognitive effort.
Okay, but I have to play devil's advocate here, because I know anyone who follows the AI space closely is probably thinking the exact same thing right now. Haven't we seen models recently that let you choose your reasoning effort?
You mean like the OpenAI O1 or O3 models?
Yeah, exactly, or the newer Qwen 3 tiers. The interface literally lets you select low, medium, or high reasoning effort. Isn't SRAM just doing the exact same thing?
That is a very common misconception, actually, but there is a fundamental difference in the architecture. Those controls you're talking about are external user-specified settings.
Oh, okay.
When you select high effort on one of those interfaces, you are forcing the model to think longer and generate more tokens, regardless of whether the specific step in the problem actually requires it. The AI has absolutely no autonomy in that decision.
Oh, I see. I'm acting as system third in that scenario. I'm the one deciding how hard the machine should think.
Precisely the issue. SRAM is revolutionary because the model itself autonomously decides turn by turn whether to dig deep or just react.
That is wild.
It dynamically adjusts to the unfolding situation without you having to turn a dial. If a math problem suddenly gets complicated in step 4, System 3 flips on the System 2 planner. If the next step is simple addition, it recognizes that, skips the heavy simulation, and just uses System 1.
It's self-aware about its own cognitive load.
Yeah.
That's incredible. But if the AI is suddenly this disciplined, how exactly did they train it to be this way? You mentioned the training regimen in our notes involved supervised fine-tuning, and then some heavy reinforcement learning algorithm with a very intimidating name.
Yeah, the training regimen is the secret sauce here. It's a two-step process. First, supervised fine-tuning, or SFT.
Right.
They essentially took reconstructed traces from a massive teacher model, DeepSeek v3.2 in this case, and used it to show the smaller model what good structured planning looks like.
Like showing a math student the answer key with all the scratch pad work written out perfectly so they learn the format.
That's a great way to look at it. But the real discipline comes from step 2 reinforcement learning, or RL, using an algorithm called GRPO with asymmetric clipping.
Okay, hold on. GRPO with asymmetric clipping. Before we lose anyone, what does that actually look like under the hood? Why is the word clipping important there?
Think of asymmetric clipping like a speed governor on a high-performance sports car engine.
Oh.
In reinforcement learning, the model gets a reward for getting the right answer, which encourages it to repeat whatever behavior led to that answer. We want it to use the System 2 planner, so we reward it for planning.
Makes sense.
But if the model starts to overthink, generating endless pages of useless planning just to chase that reward, the clipping mechanism kicks in. It cuts off the reward.
So it forces efficiency. It says, good job planning. Here's a point. Oh, you're still planning. No more points for you. You're just wasting gas.
Exactly. It penalizes the unregulated deliberation.
Here's where I get stuck, though. Even with the clipping, if the AI ultimately gets a reward for securing the right answer, doesn't reinforcement learning just naturally teach it to lean on that heavy-duty System 2 planner almost all the time?
How do you mean?
Like, wouldn't it just like, hey, planning got me the win last time. I'm just going to fire up a simulator on every single prompt just to be safe?
See, that is the exact trap standard models fall into. But the researchers found something totally counterintuitive here. Post-RL analysis showed that the frequency of planning, how often it actually invoked the System 2 simulator, only grew by 2.0 percentage points after training.
Wait, really? So it barely planned more often than it did before?
Barely at all. But the planning horizon, how far into the future it simulates when it does decide to plan, increased by 22.8%.
Whoa, so when it sits down to think, it thinks much deeper.
The AI learned to plan further ahead, not more often. When the configurator decided the situation warranted planning, it built deeper, more robust simulations of the future states. It strongly favored quality and depth over sheer quantity.
That is fascinating. So what does this mean across different types of tasks? Does it just universally plan 22% further ahead no matter what you ask it?
Not at all, and this brings us back to its autonomy. The horizon varied heavily by domain. In science tasks, the planning horizon jumped 32.7%.
Well, that makes sense. Science tasks are structured. The rules of physics don't change halfway through a chemistry problem, so you can safely simulate 10 steps ahead.
Exactly. But look at web information-seeking tasks, like browsing the internet to pull data. In that domain, the planning horizon only grew by 20.9%.
Oh, why so much lower?
The model actually learned through trial and error that the internet is chaotic. Links break, websites throw up unexpected paywalls, formatting changes. Long-term, rigid plans on the internet usually fail, so the AI learned to keep its web plans shorter and far more adaptable.
It learned that you can't plan 5 clicks ahead on the internet, because the third click might be a 404 error page. That is remarkably human. It's reading the room.
It is a level of environmental awareness that you simply don't get from unconstrained models.
To really cement how this looks in practice, let's look at exactly what happens when you give SR2AM and a standard unregulated AI the exact same problems. Let's just talk about the crocodile test, because this is a great illustration.
Oh, this is a great one. This is a scenario from the GIA Web Research Benchmark.
So the prompt given to both models is, how many non-indigenous crocodiles were found in Florida from 2000 through 2020? And they are given the specific USGS database to search. It seems like a fairly straightforward data retrieval task.
Seemingly simple, yeah.
Both models use their browser tool, they hit the USGS database, and they both successfully find the raw data, which is 6 Nile crocodiles and 1 Morris crocodile.
Right, and here is where the divergence in their cognitive architecture becomes obvious.
So the unregulated model looks at that data, immediately adds 6 plus 1, outputs 7, and fails the test. It just reacts to the first numbers it sees.
Yeah.
But SRAM handles it totally differently. Its System 3 kicks in and realizes it needs verification. Its System 2 planner literally writes out, total individuals are 7, but need to ensure no other species are present and verify years.
Notice the nuance in the language there. It's not just stating the fact. It's actively identifying the boundary of its own uncertainty.
Yes. It knows what it doesn't know. So it searches an external data set to double-check those specific years, and it discovers a patch. One of those records is from 1988.
which is outside the window.
Right. It falls outside the 2000 to 2020 window and shouldn't be counted. SRAM correctly excludes it and outputs 6.
That is the perfect illustration of System 3 overriding the urge to just spit out a fast answer and instead engaging System 2 to simulate the risk of being wrong.
There's another great example in the paper, the dodecagon test, from the AM 2024 math benchmark. The AI has to find rectangles inside a dodecagon.
Classic complex geometry problem.
Right. So the standard unregulated model tried to search the web for the answer, hit a website blocker on an AOPS math forum, and just got stuck. It spent 25 plus turns endlessly looping, trying to bypass the blocker, burning tokens, and ultimately failed.
It had no mechanism to recognize that its current strategy was a dead end. It just kept trying to smash through a brick wall.
But SRAM handled it beautifully. Before it even initiated the web search, its System 2 planner explicitly noted a fallback strategy. It wrote in its plan, if not found, enumerate computationally.
It planned for failure.
Exactly. When it hit the roadblock, it didn't panic or loop. It just pivoted to its backup plan, wrote a script, and solved the problem in just 11 messages.
Unregulated models assume success and break when they encounter reality. SRAM simulates reality, including the distinct possibility of failure, and prepares for it.
This all sounds invincible. It's efficient, it's cautious, it has backup plans. But I have to ask, does it ever fail? Like, what happens if we take away that fast, messy System I and only let it use the rigid System 2 planner? If planning is so incredibly effective, why not just force the AI to do it all the time?
That is a great theoretical question, and the researchers actually ran an ablation study to test exactly that. They systematically removed different components of the architecture to see what would break.
So what happened when they turned off System More?
Taking away systemized freeform reasoning caused the biggest accuracy drop of the entire study. The overall pass at one score plummeted from 66.6 down to 46.8.
Wow. So making it purely logical and forcing it to plan everything actually made it significantly dumber.
Yeah. If we connect this to the bigger picture, it proves that true intelligence requires both. It needs the structured simulative planner, absolutely, but it also desperately needs the messy, human-like intuition of freeform reasoning to succeed.
Because otherwise it just gets bogged down.
Exactly. If you force it to perfectly structure every single thought, it loses the ability to make intuitive leaps or handle fine-grained, in-the-moment execution. It gets paralyzed by its own rigid structure.
It needs the driver's gut instinct just as much as it needs the GPS.
Nailed it. Furthermore, they tested what happens if you take away System 3, the configurator. And as you might expect based on our earlier discussion, without System 3, the model reverted back to unregulated deliberation.
It just started rambling again.
It started burning tokens endlessly again, losing all of the efficiency gains. It is the synergy between all three systems that creates the magic.
So, bringing this all together, SRAM represents a massive leap forward. We are breaking AI out of this endless, expensive chain of thought loop. We're giving it a true human-like balance of reaction, simulation, and self-regulation. It's faster, it's cheaper to run, and in many ways, it's actually smarter because it knows when to try hard.
It is a profound shift in machine cognitive architecture. And this raises a very important question, which the researchers touch on in their conclusion. And I think it's something you, the listener, should really mull over as this technology evolves.
Wait on this.
Right now, this System 3 configurator is just being used to regulate inference time planning. It's simply deciding how to answer a single immediate prompt.
Okay.
But if an AI can successfully regulate its own reasoning process, what happens when we apply this same self-regulation to how an agent governs its own learning over time?
Oh, wow.
Could a future version of System 3 allow an AI to autonomously revise its own long-term goals? Could it decide, entirely on its own, when it needs to retreat into mental simulation to update its entire worldview based on new evidence it encountered that day?
That is wild to think about.
We're looking at a massive stepping stone toward true, independent machine agency. Not just machines that know how to think, but machines that know how to manage their own cognitive development.
That is both incredible and slightly terrifying to think about. An AI that decides when it's time to sit down, process the day, and rethink its life choices based on a mental simulation.
It's the dawn of a very different, very deliberate kind of artificial intelligence.
Well, keep an eye out for these self-regulating models because they're going to fundamentally change the landscape of what AI can do and how much power it takes to do it. Next time you see an AI spinning its wheels, writing a novel to answer a simple question, just remember it's doing that because it doesn't have a System 3 yet. Thanks for joining us on this deep dive into the architecture of machine thought. Catch you next time.